segment, we're going to talk about the Otto cycle, and the Otto cycle is used to model the spark ignition engine. But before we get there, let's go ahead and take a minute to review the first law of thermodynamics. So the first law says that the change in energy stored by the system is equal to the net amount of energy transferred into the system across the boundary. So the change in energy stored by the system, delta E, well, we know from Thermodynamics 1 that energy could be stored by the system in three ways: by internal energy, kinetic energy, and potential energy. Then we've got the right-hand side of the equation. So it's the sum of all the energy coming in minus all the energy going out. In Thermo 1, we typically used the sign convention to dictate whether heat and work were crossing the system boundary into the system or out of the system. But when we talk about cycles, it's much more convenient to use the subscript convention. And we're going to look at both of these cases, but if you do need a review, there are a couple of Thermodynamics 1 videos that may be useful for you. So with the spark ignition engine, this is a piston cylinder type of arrangement. So we're going to model these as closed systems. So let's look at that first law for a closed system. This is the one that you're most familiar with. This is the sign convention. So you've got the change in energy stored by the system on the left-hand side, and then you've got this Q minus W on the right-hand side. And the sign of Q and W are going to tell you whether it's going into or out of the system. Subscript convention looks exactly the same on the left-hand side, but on the right-hand side, instead of having Q minus W, you sort of tease things out, and it's Q in minus Q out minus work in. And all of those Q and W terms are positive quantities. All right, so here's our spark ignition engine. We've got 4 strokes. Now, we could talk about a 2-stroke engine as well, gasoline spark ignition engine as well. That would be used for smaller devices, like it's used in motorcycles, it's used in lawn equipment, that sort of thing as well. But we're going to focus specifically on this 4-stroke engine. So as this piston pulls down, the intake valve opens, and what comes in is air and fuel. Then you have the compression stroke where that piston head comes back up. Once it gets to top dead center, spark goes off and it ignites that air-fuel mixture, forcing that piston head down. That's where you get your power output. And then the exhaust stroke is where that piston head comes back up, the exhaust valve opens, and the products of exhaust leave, or the products of combustion leave the system. So it's not a true thermodynamic cycle, because what you start with in the first process is air and fuel, and what you end up with during the exhaust stroke are the products of combustion. If you're combusting a hydrocarbon fuel with air, you'll get CO2, you'll get water, you'll get nitrogen, you'll get some other stuff as well. So it's not a true thermodynamic cycle, because the state at state 1 is not the state at the final state, right? Because you got completely different substances. But it is something that we can model as a thermodynamic cycle. So we're making a lot of assumptions here. We're simplifying this. It's a model, so just keep that in mind. It's a model of the actual process. And we can get some important information. We can estimate the work net output, things like that we would be interested in for a spark ignition engine. All right, so our ideal Otto cycle, this is our very simplified model for what's going on with a spark ignition engine. So we've got a piston cylinder type of arrangement, and our working fluid, we're going to say that our working fluid is air. So remember those air standard assumptions. Our working fluid is air, and we start out at bottom dead center, and we're going to follow this cycle on a PV and a TV diagram. So from state 1 to state 2, you have an isentropic expansion or compression. From 2 to 3, you have a constant volume heat addition. 3 to 4, you have an isentropic expansion. And 4 to 1, you have a constant volume heat rejection process. Those heat addition and heat rejection processes are the processes that we are using to model the combustion process and the exhaust process. So let's look at all 4 of those processes, and we're going to talk about the tools that we have to analyze those processes. So state 1 to 2, you have an isentropic expansion. We're going to make the assumptions that we've got, or we're going to make air standard assumptions first, and we're going to apply our first law. We've got a piston cylinder, that's our model, with air in it, and So I'm applying the first law for a closed system. And as you often did with piston cylinders in Thermo 1, we're just going to ignore the kinetic and potential energy changes. It's an isentropic expansion, which means that it's adiabatic and reversible, so those Q terms go away, and it's a compression process. So that means that we have to put work into it, not get work out. So I'm going to get rid of that work out, and all I'm left with is that the work in is equal to delta U, which in this case is U2 minus U1, and that's my first law. Now, the other thing that goes along with those air standard assumptions is that I have air and it behaves like an ideal gas, so I can use my ideal gas law. And because it behaves as an ideal gas at state 1 and state 2, I can put both of these quantities equal to one another because they're both equal to 1. We can also use those isentropic relationships because I have an ideal gas undergoing an isentropic process. So I've got two forms that I can use, one in terms of relative specific volumes, one in terms of relative pressures if I wanted to. And these two equations are used if we're not making any assumptions about specific heats being constant. If we do make the assumption that specific heats are constant, in other words, we're making cold air standard assumptions, then I can replace that delta U with CV delta T, and I can also use the isentropic relationships that are specific for that assumption. So this is for an ideal gas undergoing an isentropic process if we assume that specific heats are constant. All right, so now let's look at the second process. We've got a constant volume heat addition process. So if I apply my first law, and you'll notice that I've ignored the kinetic and potential energy changes. I'm going to do that for the remainder of this cycle. So I've got a constant volume process, which means that I don't have any work, and I also don't have any Q out. I've just got a Q in. So when I cancel everything out except the Q in, I've got Q in is equal to delta U, which in this case is it's what it is after minus what it is before. So U3 minus U2. All right, so there's my first law. I've also still got an ideal gas, so I can apply the ideal gas law between 2 and 3. And if cold air standard assumptions are used, I can put that delta U in terms of a CV delta T. And that's it. I can't really use any isentropic relationships for state 2 to 3 because I do not have an isentropic process. So from 3 to 4, I do have an isentropic expansion. So if I apply the first law, and I ignore kinetic and potential energy changes, well, number one, it's isentropic, which means that it's adiabatic, Q is 0, and it's reversible. So I'll get rid of the Q's. And then because it's an expansion process, that's a work out, not a work in. So I cancel everything out, everything except that work out term. And what I'll have is my work out is equal to negative delta U, which in this case would be U3 minus U4. So delta U would be what it is after minus what it is before, U4 minus U3, but the negative makes it U3 minus U4. So there's my first law. I can still use my ideal gas law because I've got an ideal gas, so I'm doing it between 3 and 4. And I can use isentropic relationships because I have an isentropic process. Now, if I made cold air standard assumptions, then I could put that delta U in terms of CV delta T. So in this case, it would be CV times T3 minus T4. And I could replace those two isentropic relationships with the relative specific volumes and the relative pressures in terms of just temperature, pressure, and specific volume. And I can directly calculate things. All right, one more process left, constant volume heat rejection process. So if I apply my first law, I've got, well, it's a constant volume process, so I have no boundary work and no other type of work going on. So the work out and work in terms are going to go away. And I have and I've got a Q out, not a Q in, so that's going to go away. And all I've got left is Q out is equal to negative delta U. And delta U, it's what it is after minus what it is before. And what it is after in this case is 1, state 1, and what it is before is 4. So because you're going from state 4 back to state 1. So my delta U ends up being U1 minus U4, and then the negative would make it U4 minus U1. I can still use my ideal gas law, no problem. There we go. I can't use any isentropic relationships because I don't have an isentropic process. But if I do make cold air standard assumptions, I absolutely can put that delta U in terms of CV delta T. All right, well, I hope that was very helpful, and we'll work some problems with this the next time that we meet. Thank you for watching.